Hello and welcome to an introduction to support vector machines, the classifiers that maximize margin. In this talk we assume that you have a basic understanding of linear classifiers such as perceptrons. If you do not have that, this might be a good time to brush up the basics. Now all the examples presented in this tutorial will be in 2 dimensions, which makes it easier for us to draw and visualize. However, any theory that we talk about will readily generalize to higher dimensional spaces. So let's consider an example of two classes, the points in red belonging to one class and the points in blue belonging to a second class. Now the goal of perceptron learning is to find a line that would separate these two classes. Now, as you can clearly see, there are multiple solutions that can separate these set of points. For example, this blue line might as well separate these points, or this green line. And perceptron learning, or any gradient descent method for that matter, results in a feasible solution. That means the resulting line that an algorithm finds, a learning algorithm finds, will be or could be any of the set of feasible solutions that are present in this space between the two set of points. Now in this case you have a large number of such lines, which goes anywhere from the blue line through the green line to the brown line that we have shown here. Now the question that we are asking here is, are all these solutions equally good? Well, we might have a feeling, an intuition, that maybe the green line is somehow better than the red line or the blue line here, due to the fact that the green line is in fact farther away from all the sets of points, and hence it is likely to correctly classify a future point which might be slightly different from what is existing in the training samples. To formalize the idea of goodness of a solution, we will first introduce a term called margin. A margin is defined as the width of a band around the decision boundary without any training samples in it. For example, in the case of the red line here, there exists a band around the red line indicated by the two thin red lines on either side. Inside that band there are no training samples present. The width of this band is what we refer to as the margin of this particular decision boundary. Now we will refer to this width as margin 1 for the red line. Now let's take a look at what would have been the margin for the other examples that we had seen before. For example, if you take this blue line, the margin would be slightly smaller and here indicated as margin 2. And of course for the green line that we saw before, the width of the margin around it is much larger, here referred to as margin 3. Now if you compare margin 1, 2 and 3, it's obvious to see that margin 3 is much larger than margins 1 and 2. And hence maybe we can capture the idea of optimal solution in terms of how good or how big the margin is. Now you would notice that the margin varies with the position and orientation of the separating hyperplane, and the goal that we have stated in terms of optimizing the decision boundary would now be restated as a decision boundary that would maximize the margin around it. Now the natural question to ask is the larger margin better, which is what we had intuitively felt, or better, why is it better? So that question is what we need to answer, and it can be answered now formally. Now before going forward with that, we will take a slightly different look at the same concept of margin. Now instead of thinking of margins as bands around a decision boundary, we will start to think of margin as a small region around each of the training samples through which the decision boundary cannot pass. Say for example, if we have a set of small circles that encompass each of those training samples, you would notice that the red line and the blue line is in fact passing through some of these circles. And if you want to avoid that, we need to move the red and blue lines a little bit, such as here. Now, the set of possible lines that can lie between the two classes has reduced, or the feasible solution region has reduced. Now, if we increase the radius of the circles further, you would notice that once again we will need to move the blue line and the red line to make sure that it does not pass through the bubbles. So as the margin increases, the feasible region reduces, and it keeps on increase as the radius keeps on increasing. You notice that the feasible region keeps on reducing until a point where all the feasible regions get squeezed into a single line. Now at this point we cannot increase the radiuses of the bubbles anymore. If you do that, then the feasible region will reduce to zero and you cannot find a solution that would not pass through any of the bubbles. Now another point that you might note is that not every circle around these training samples are touching the decision boundary at this point. Most of the circles which are farther away to the right and to the left are quite far away from the decision boundary, and there are only a few training samples which in fact touch the decision boundary. Now these are the ones which actually control the decision boundary. And in the theory of support vector machines, we call the samples whose bubbles are touching the decision boundary as the support vectors. Now we can compare the ideas of the band and the bubble, uh, two different interpretations of margins, and we readily see that they are actually one and the same. For example, if you look at this set of bubbles around the support vectors, and if you take the band interpretation of the margin, you would notice that the bands will actually touch the same support vectors as what we saw in the bubble interpretation. And the margin, let's denote it as rho, is in fact twice the radius of the bubbles that were around the support vectors. If the radius is r, the margin rho would be 2r. And as we mentioned before, the samples that support the decision boundary are called the support vectors. And both interpretations of margin, whether it's the band interpretation or the bubble interpretation, would lead to the same decision boundary when we maximize these. Now we had made an intuitive assertion that maximizing the margin is probably a good idea. And the justification for that, what we said, was that if the margin is large, then future test samples are unlikely to cross over the decision boundaries. Now this is in fact far more than a simple intuition. In fact, this was formally proved by two Russian mathematicians, Vladimir Vapnik and Alexei Chernovenkis, in the 1970s. And this theory, developed by the two mathematicians, popularly known as VC dimension by the starting letters of their names, in fact forms the basis of most of modern machine learning theory. Now, this theory in fact resulted in a really startling result, which states that there is a bound existing on the expected loss of future test samples, also known as risk in the Bayesian learning theory. So the result that we will state directly is that the risk R of alpha, alpha is a decision boundary that we compute, will be less than equal to the risk or the error that we make during training plus a function of a variable called h, square root of f of h by n. Now if you look closely into this equation, there is something dramatically new in this equation. On the left hand side, what we have is the risk or the expected loss of future test samples. Now this theory is making a prediction that in future whatever loss that can occur from the decision boundary is bounded by two factors. One is the training error and the second is a function f of h, where h is in fact what you refer to as the VC dimension, and f of h is in fact h plus h times log 2n minus h times log h minus c. Well, we will not worry too much about the exact form of the function, but we will notice that the in the first equation, the second term square root of f of h by n is in fact a monotonically increasing function. That is, as h increases, the value of square root of f of h by n will increase. So let's understand this equation once again. What we are saying is that the equation gives you a guarantee that your future test error of unknown samples that you've never seen is bounded by or will be less than equal to your training error plus a monotonically increasing function of h. Now this was a huge breakthrough in machine learning, where now you have a bound on the test error from the training error, which in fact is not that big in terms of what it says right now, because yes, there are other theories such as the Bayesian learning theory which would give such bounds. However, what is more important is what f of h means. We will take a look at that now. So let's understand what f of h is and why maximizing the margin is a good idea. Now our goal is to reduce the future test error, and we notice that to reduce the future test error we need to keep the training error low, or let's say 0, and then minimize the VC dimension h. If we can do that, then we have achieved the goal of reducing the test error. Now let's see what h is in terms of the samples that we have. Let's assume that we have a set of training samples and a decision boundary shown in green here and the corresponding margin around it. Let's say the margin is rho. Now there is a small problem with margin, that the actual value of this width of this margin is dependent on the scale of the points. That is, if I scale all the points up, then the margin will increase. But that doesn't really change the actual layout of points inside the space. So what we will do is we will define what we call as a relative margin instead of the absolute margin. To do that, we will consider a sphere that, in this case, in two-dimensional case, a circle that encompasses all the points. Now if you take the smallest sphere that encompasses all the training samples, and let's say the diameter of that sphere is d, then the relative margin of this set of points and the decision boundary would be given by rho by d. So this way we will make the margin independent of the scale of the points. So once we understand rho by d as the actual margin between this set of training samples, our goal is to maximize this. So instead of maximizing absolute margin, we will talk about maximizing the relative margin. That way we will get around the problem of scale. Now the VC dimension h is given by the equation below. H is less than equal to min of two quantities, d, the dimensionality of the set of points, and the CEAL of d square by rho square, which is the inverse of relative margin squared, plus 1. Now let's understand this equation a little closer. You have two terms here. One is the min term and there's a plus 1. So anyway, the plus 1 doesn't affect the overall VC dimension. It's there always. So let's understand the first part of it. Now what is interesting to note here is that the VC dimension h depends on two factors. One is the dimensionality of the set of points, and the second is what we just defined as the relative margin. And what is even more interesting is that now we have the equation of h dependent on dimensionality, but it is minimum of either dimensionality or this relative margin squared. Now this is extremely important once you understand the implication of it. The idea is that if somehow if we can reduce the second term d square by rho square CL of that below the dimensionality d, then the actual value of d does not matter anymore for the VC dimension. That is, even if the dimensionality is extremely large, our VC dimension will be bounded, upper bounded by d square by rho square. Now this is a huge breakthrough in machine learning. What people always used to refer to as the curse of dimensionality, which referred to the fact that when the dimensionality goes up, our test error keeps going up, and there's no way to control this. This is in fact also related to what you call as overfitting, or what reduces the generalization error. But now the theory of VC dimension gives us a handle to break this curse. What we are saying is that let's not even worry about D. If somehow we can reduce the relative margin in such a way that d square by rho square falls below the dimensionality d, then it doesn't matter what d is, we can let it grow as much as we want, and the VC dimension h would be bounded by d square by rho square. Now if this is the case, then our from the previous equations we notice that the function that dependent on the VC dimension will become low, and the test error hence would be bounded by this function of VC dimension, and that would now be independent of D. And this, as I mentioned, allows us to break the curse of dimensionality, and this forms one of the most fundamental principles of maximum margin classification. So once again, to reiterate, maximizing the margin improves generalization, and h can be made independent of the dimensionality d by reducing the quantity d square by rho square, or maximizing the relative margin. So now that we have introduced a formal justification as to why we want to maximize the margin, let us try to derive a method to do so. And to do that, we will first introduce some formalism. Let's assume that we have a set of training samples, and let's say we have a decision boundary that we are considering, and the equation of the decision boundary would be given by W transpose X plus B equal to 0, where W are the coefficients of the hyperplane, and B is the constant term, X is the training sample here, and let the two lines parallel to the decision boundary which controls the margin be W transpose X plus B is equal to plus or minus epsilon, which would indicate that the margin is 2 epsilon. Note that the value of W transpose X plus B is dependent on the scale of X and W. This is the same problem that we referred to before, and that's the reason why we define the relative margin. However, while deriving the method for computing the decision boundary, we will approach it in a slightly different way, and hence the point that we are noting is that W transpose Xi plus B is dependent on the scale of X and W. To introduce a bit more of formalization, we will denote the W transpose X plus B term as a function g of X, which would make the writing easier. The decision boundary will now be denoted by g of X equal to 0. The two extremes of the margin would be given by g of x equal to minus k and g of x equal to k, or what we referred to as epsilon before. Now we just denoted it as k, where w is a vector that is perpendicular to the decision boundary. The margin now is 2k. Now what we want is to maximize the margin, or maximize k in this case, or in such a way that W transpose xi plus b is greater than k for the samples of one class for which di equal to 1, that is the sign of the samples is plus 1, and for the second class we want W transpose xi plus b to be less than minus k, less than equal to minus k, for those samples for which di equal to minus 1. So di is the label of the samples, which is either plus 1 for one class and minus 1 for the second class. Now, as we noted before, the value of g of x will depend on the scale of w. And to control the scale, there are two ways in which we can do this. We can say, in the first case, we can keep the norm of w equal to 1 and then try to maximize the margin, in this case maximize g of x, such that we will get maximum margin. Or we can let g of x should be greater than equal to 1 and then try to minimize mod w. Both are valid ways of doing the same thing. You note that if you keep the scale of samples the same and then try to maximize the margin, the relative margin will increase. A second way to do that is keep the margin constant and reduce the scale of the samples. That way also the relative margin will get maximized. So these are the two approaches that we are talking about. In the first case, we are saying let the scale of the samples be the same and then try to maximize g of x. Or in the second case, we are saying let the scale of the points remain, the margin be 1 fixed, and let the scale of points reduce. And in both cases, we are in fact trying to maximize the relative margin. And for certain notational conveniences, we will take the second approach in this case. So we will use the approach 2 and formulate the problem as we want to minimize mode of w, the norm of w. The norm of w is nothing but w transpose w. We will just introduce a term, half of it, for mathematical convenience at a later stage. We will note that this is just the same as norm of w, just half of that quantity. So we want to minimize this quantity, half of w transpose w, subject to the condition that w transpose xi plus b should be greater than 1 for positive samples and less than minus 1 for the negative samples. And we can actually write those two conditions together as di times w transpose xi plus b should be greater than equal to 1 for all the samples. This would allow us to minimize the margin subject to a set of linear inequalities. So let's try to write this optimization problem. Our goal is to minimize the quantity phi of w, which is half of w transpose w, and subject to the condition that di times w transpose xi plus b minus 1 should be greater than equal to 0, which is for all I. This is exactly the same thing that we said before, stated slightly differently. Now what we have here is a quadratic objective function with a set of linear inequalities as constraints. And there are solutions such as QP solvers which can do this. But before doing this, we will try to modify and write the problem slightly differently. So first what we will do is we will try to integrate the constraints into the minimization using the Lagrangian form, which, if you don't know the method of Lagrange multipliers, you might want to look it up. The idea is that the constraints stated in the form of a set of linear equalities or inequalities equal to 0 will now appear as terms inside the function to be minimized. So the new function to be minimized, we will state as j of w, b, and alpha, where w and b are the parameters of the hyperplane that we need to learn, and alpha are a set of new parameters that are introduced by the method of Lagrange multipliers. Alphas are in fact what you call as Lagrange multipliers. So what we need to minimize now is j of w b alpha is equal to half of w transpose w, the term that we had defined before, plus or minus in this case the terms that appear from the constraints. So in this case you will have n number of terms that appear from each of the training samples, and hence an addition of all those samples will appear as Lagrange terms, Lagrange multiplier terms. So in this case this is sum of I goes from 1 to n of alpha I di w transpose xi plus b plus sigma I equal to 1 to n alpha I. This is essentially the actual function that we wanted to minimize phi of w minus alpha I times the constraint that we wrote before, and that constraint will appear for each of the training samples and hence the summation. Now there are a couple of conditions that are still left out. The method of Lagrange multipliers insists that the Lagrange multipliers should all be positive or non-negative, and hence alpha I should be greater than or equal to 0 for all I. So this is the new function that we would like to minimize. Now once again, before doing this, we will try to modify this a little bit. However, this is the problem that we really need to solve, and the method of Lagrange multipliers will state that this function has to be minimized with respect to w and b as before, but it has to be maximized with respect to alpha, and that's how it turns out to be as a result of the method of Lagrange multipliers. We will not get into it. However, if you notice what this means, this function j is a function that lives in a high dimensional space. It's difficult to draw very high dimensional spaces, so we will just take a look at it as a two-dimensional space. The axis corresponding to w and b, we will shrink it into a single axis, and the axis corresponding to alpha we will shrink into a second axis. So in this case, the two horizontal axes on the ground correspond to, one corresponds to w and b, and the second corresponds to alpha. And what we would notice is that the point that we want to seek is a point at which the function is a minimum with respect to w and b, and it is a maximum with respect to alpha. So this point is what we refer to as a saddle point, such as what is mentioned here. So you notice that at that point the function is a minimum in one direction and a maximum in the orthogonal dimension. So this is what we refer to as a saddle point. Of course, the shape of the function at this point looks like a horse saddle, and hence the name. What we want to find out is the saddle point in this function j. Now let's try to understand this function j a little better. This is the objective function once again written. It is half of w transpose w minus sigma I equal to 1 to n alpha I di w transpose xi plus b plus sigma I equal to 1 to n alpha. It's the same equation that we took from the previous slide. And what we would like to do is, this function is what we refer to as the primal form that we want to minimize in optimization. And in the theory of optimization, there is the concept called a primal form and a dual form of a function to optimize. And almost any problem that you think about, or there are many such problems for which the same problem can be stated in the primal form or the dual form. And it so happens that in some cases the primal form is easier to solve, whereas in other cases the dual form is easier to solve. Both are the same problem. The solutions to both the primal form and the dual form are exactly the same. However, the way in which it is stated, the dual form is sometimes easier to solve than the primal form. And it so happens that in this case, the dual form is easier to solve, and hence we will try to derive the dual form of this function to optimize. To do that, what we are going to do is we will first take a look at the function to optimize, the j function. It's a function of three variables, w, b, and alpha. And from basic calculus, you would notice that if you find a minimum of this function, or a maximum for that matter, the derivative of the function with respect to its variables should be 0. This is true from calculus. So at the optimum, uh, condition 1 is that dou j by dou w equal to 0. The partial derivative of j with respect to w should be 0, and the partial derivative of j with respect to b should be 0. Of course, the partial derivative with respect to alpha should also be 0, but we will consider only these two conditions for now. So let's try to take these two conditions and see what they mean. So let's take the first one, that is the partial derivative of j with respect to w at the optimum should be 0. So if I take the j function and differentiate it with respect to w, you would notice that for the first term, this is of the form w transpose w, which is something like w square, and the derivative of that would be 2w with the half term, that would turn out to be w. And in the third term there is no w, and hence that would vanish. And in the second term there are actually two parts, the first part containing w, and the second part without a w. So if I differentiate this whole thing, you will get, and set it to 0, you will get the condition that the value of w at the optimum, which we would denote as wo, or w optimum, is equal to summation I equal to 1 to n of alpha I di xi. We can see this easily by differentiating the above function j. Now this is interesting to note. What it says is that, remember that xi's are the training samples, di's are the labels of the training samples, and alpha i's are the Lagrange multipliers that we had just defined before. And these are just scalars, which are non-negative scalars. What we are saying is our equation of the optimal hyperplane W is nothing but a linear combination of the training samples weighted by the Lagrange multipliers alpha I with the sign di. And that's an interesting point to note, that even after all this optimal theory, what we will obtain is that our decision boundary, the optimal decision boundary WO, is nothing but a linear combination of the training samples. It's an interesting point to note right now. We will keep it at that. Now if you take the second condition, that is the partial derivative of j with respect to b should be 0, and try to do the same. If I differentiate the j function with respect to b, the first term will go to 0, the third term will go to 0, neither of them contains any b, and the second term, if I differentiate with respect to b, you would be left out with sigma I equal to 1 to n alpha I di, and we note that that has to go to 0 at the optimum. That is, the partial derivative of j with respect to b should be 0, yields us the condition that sigma I equal to 1 to n alpha I di equal to 0. Or in other words, if I sum up all the Lagrange multipliers alpha I multiplied by the sign of the corresponding training samples, then you should get 0. Or in other words, all the Lagrange multipliers of the positive class should sum up to the same value as all the Lagrange multipliers of the negative class. Again, a useful condition that we will see later on. Now, in addition to these two conditions, which we obtain by setting the partial derivative of j with respect to w and b to 0, we have a set of conditions that come up from the theory of Lagrange multipliers and optimization, which is usually referred to as KKT conditions. KKT actually refers to the names of three people, Karush, Kuhn, and Tucker, and those three people were instrumental in developing the theory, and hence referred to as KKT conditions, or sometimes just referred to as Kuhn-Tucker conditions. So the Kuhn-Tucker conditions state that at the optimum, all the terms corresponding to Lagrange multipliers, that is each and every term corresponding to the Lagrange multipliers in the J function should go to 0 at the optimum. So taking a closer look at it, if I take each of those terms corresponding to each of the training samples, what we have is alpha I times di times W optimum transpose xi plus B optimum minus 1 should be 0 for every I. That is, for every training sample at the optimum, this term should vanish. Now that's interesting. What it says is that, let's take a closer look at that condition. What does that say? How can this term go to 0? Well, if you look at it, there are two ways in which you can make this term 0. By putting alpha I equal to 0, that's one way, the whole term will become 0 in that case. Or if alpha is not 0, then the second part of that term should go to 0. That is, di times wo transpose xi plus bo should become 1. Now what does that second condition mean? When we say that di times w transpose xi plus b should be 1, remember what di times w transpose xi plus b is. This was g of x. This was what controlled the margin. So what it tells us is that if alpha I is non-zero, then for that particular sample, your W transpose xi plus B should be either plus 1 or minus 1, depending on the sign di. That means these are the samples that actually touch the margin, or these are in fact the support vectors. So let's try to understand this once again. What we said is, if alpha I equal to 0, then we don't have any constraint on xi, or rather wo or b. However, if alpha is non-zero, then this sample has to touch the margin exactly, or these samples should be support vectors. Once again, alpha I is 0, the samples may not be support vectors, but if alpha I is non-zero, then the sample should be support vectors. So this is a very useful equation to have, because once we give this function to optimize to a optimizing algorithm, it will come back with a bunch of alpha i's, and out of these alpha i's, most of these alpha i's would be 0, and they will not be uh, related to the support vectors. But for a few training samples, alpha I will be non-zero, and those would correspond to the support vectors. So this is very useful, as we would see in later on. Now let's just take these conditions that we derived, 1, 2, and 3, try to substitute it back into the objective function j. If we expand it with a little bit of manipulation, you can see that j of wb alpha is equal to sigma equal to 1 to n alpha I, which is exactly the same term as the third term before. I just wrote it at the beginning. Then you have the second term, which is same as the first term before, half of alpha w transpose w. Now the third term is in this equation j is actually the second term from before, but expanded a bit. It is the w is independent of I, and hence I took it out. You can write it as w transpose sigma I equal to 1 to n alpha I di xi minus b times sigma I equal to 1 to n alpha I di. Now if you take a look at it, the last term here, which is b times sigma I equal to 1 to n alpha I di, well, by condition 2 above, sigma I equal to 1 to n alpha I di is 0. Hence, the last term in this thing will go to 0. So that's simplified. Now the last but one term, you had w transpose sigma I equal to 1 to n alpha I di xi, but at the optimum, sigma I equal to 1 to n alpha I di xi is w optimum, which is given by condition 1. So this is nothing but w transpose w. So what you have is sigma I equal to 1 to n alpha I plus half of w transpose w minus w transpose w. So the second and third terms will again combine to give you a negative half of w transpose w. which we can expand it further by substituting for w, and what you would get is a new function which is same as j. We would just call it as q. Q of alpha is sigma I equal to 1 to n alpha I, which is same as the first term from before, and the second is minus half of w transpose w, which is minus half of each w would be rewritten as alpha I di xi. So what you have is minus half of sigma I equal to 1 to n, sigma j equal to 1 to n, alpha I alpha j, di dj, and xi transpose xj. So this is the new function to minimize. This is exactly the same as j, but now rewritten slightly differently and is referred to as the dual form of the function j. What you would note is that the q function has only alpha i's in it. All the other parameters that we had, all the other unknowns that we had, w and b, has vanished now. This is a function purely of the variable alphas. Remember, di and dj are labels of the training samples that we know already, so they are constants. Xi's and xj's are training samples, hence xi transpose xj is a constant. For any I and j, xi transpose xj is nothing but a scalar. So this is a simple scalar function of alpha, which is nothing but sigma I equal to 1 to n alpha I minus half of sigma I equal to 1 to n, sigma j equal to 1 to n, alpha I alpha j. So it's a quadratic in alpha. Remember, di dj xi transpose xj will hold combined to become a single constant. So it's a very simple equation, or rather function, to optimize now. Now remember, we noticed before that the j function has to be minimized with respect to w and b and has to be maximized with respect to alpha. So now we have a function q which has to be maximized with respect to alpha. So the new dual function to optimize can now be written as q of alpha is sigma I equal to 1 to n alpha I minus half of I equal to 1 to n, j goes from 1 to n, alpha I alpha j, di dj, xi transpose xj. Now the conditions are not completely gone. We remember that for the method of Lagrange multipliers, alpha had to be positive or non-negative. Hence, all the alpha I should be greater than or equal to 0. And the condition on alpha I that we had derived before, that is sigma I equal to 1 to n, alpha I di should also be 0. So these are the new function to be optimized and the corresponding constraints to be obeyed. Now we notice that the only unknowns here, or the variables here, are alpha i's, and the constraints are also on alpha i's only. There are no w's or b's in this formulation anymore. So this is exactly same as j before, slightly rewritten in a different form, and we call this the dual form. And usually, if the primal form is a minimization problem, the dual is usually a maximization problem. So we have q of alpha, which has to be maximized with respect to alpha. This has to be solved. We won't get into details of how to solve this, but this again is a quadratic function in alpha with linear inequalities as constraints. And to solve this, you can take the help of any of the QP solvers that are available from the theory of optimization, which is one of the factors that really contributed to the popularity of support vector machines in the recent past. The theory, if you remember, the theory of VC dimension has been around for some time, from 1970s, but it was only in 1990s that the theory of optimizations became strong enough to provide us with methods to solve these problems efficiently. So this comes under the category of convex optimization. It's a convex function to be optimized subject to linear inequalities, and it can be solved using a set of known methods from the theory of optimization. We note that the data vectors only appear as dot products in this, and the objective function to maximize in this case is convex and subject to a set of linear constraints, and it can be solved using standard convex quadratic program solvers. So we will not get into details of how to solve this. What we would make use of is a black box of QP solver. So we give this problem to a QP solver and out pops a bunch of constants alpha i's as the solution to this maximization problem. And once we have alpha i's, which are the Lagrange multipliers, we had commented before that most of these alpha i's would be 0, which would correspond to the non-support vectors, and there will be some alpha i's which are non-zero, which will correspond to the support vectors. And we can write W in terms of alpha i's. Remember from the previous slide we had W optimum is sigma I equal to 1 to n alpha I di xi. Remember xi's are the training samples, we know those. Di's are the corresponding labels, we know those. Alpha i's are the Lagrange multipliers which we just got out of the QP solver, and hence we know those also. So hence we can write the optimal hyperplane WO is equal to sigma I equal to 1 to n alpha I di xi, which is a linear combination of the training samples. But if you look a little closer, remember that these alpha i's are 0 for non-support vectors. Hence, what we are saying is the optimal hyperplane is in fact written as a linear combination of only the support vectors. For others, the alpha i's would be 0. So this is how what we intuitively said at the beginning, that there are a few samples that actually control the optimal decision boundary. Those, the bubbles around which was squeezing the optimal hyperplane, or those were the samples which, when we tried to maximize the band around the training samples, which went and touched the training samples, those were the support vectors, and those were the intuitive pictures that we developed. Now from the theory, what we note is that it is exactly those samples which would define the optimal decision boundary, and hence W optimum is written as a linear combination of exactly those support vectors. Now once we get W optimum, we can also find B optimum, which is not so difficult to find because the Kuhn-Tucker condition stated that alpha I times di times W transpose xi plus B minus 1 should be 0. And if I take any of the training samples for which alpha I is non-zero, that is, if I take any of the support vectors, and for convenience, let's say I'll take a support vector from the positive class, that is, for which di is equal to plus 1. So if alpha I is non-zero, then I can divide both sides by alpha I, and alpha I would vanish. I can assume that di equal to plus 1 if I take a training sample xi belonging to the positive class. So hence di is also goes to 1. I don't have to worry about that. The equation simply becomes W optimum transpose xi plus b should be equal to 1. Or in other words, I will be able to write the value of b as 1 minus W transpose x, where x is a support vector from the positive class, and hence I have written it as x as plus. So take any support vector from the positive class, and your optimal b can now be computed as 1 minus W transpose x as plus. So now you have computed both W optimum and B optimum, which means now we have complete understanding of the optimum decision boundary between the two classes that we started out with. So now with the tools that are available to us in the form of convex optimization toolkits, we have now a method to derive the optimal decision boundary between two sets of classes that would maximize the relative margin. And we know that maximizing the relative margin will yield us the most generalizable solution, that is, which would reduce the testing error. From the method, from the theory of VC dimension, we have proved that. So together with, now we have both the theory and a practical method to achieve this. And the second thing that is beautiful about this method is that this is a convex optimization function, and it is not like gradient descent methods which would get stuck in local minima. Quadratic functions or convex functions using convex optimization will guarantee us the optimal solution, and hence we will always arrive at the optimal hyperplane that would separate two sets of training samples in terms of maximizing the margin.